So welcome back. Today we will do a tutorial on network structure. So you've already been introduced to NetworkX, which is a very powerful Python package for analyzing various kinds of networks. We'll again go through some of the basics of NetworkX and look at how we would connect, look at how we would generate undirected, directed and weighted graphs. How do we access various elements of these graphs in NetworkX and perform visualizations, compute various network parameters, and also a handful of centrality measures. I presume that you also by this time know how to build a Jupyter notebook and how do you set it up in whatever environment you are comfortable with. You see that here I am using Visual Studio Code to run the Jupyter notebook. I have already created I've opened a Jupyter notebook server, right. I use Miniconda in this case. You can use whatever that fits you and whatever works on your system. But if you need some help, please feel to reach out and we'll help you with the installation of these as well. So the first step is to import NumPy because it typically is found useful, and matplotlib for plotting, and then NetworkX as NX. This is a standard way to import these packages. NetworkX is the most important package here, so let me run this again, and it ran fairly quickly because I had already run it once. And now I want to generate a graph that looks like this. So this graph has edges, so this you may remember from the slides, and this graph has edges like AB, AC, AD, and BC, BD, DE, CD, DF, EF, and so on, right, and also BG. So all these edges are captured in this list of edges, and now you first create. So you say nx.graph, create a graph object, and make this list of tuples of pairs of nodes that form edges, and then use this interesting command called add edges from. So okay. Okay, so it says the output exceeds the size limit here and could open the full data, but basically I was trying to also get you the help for this. So maybe let's do that separately. Maybe I can add an edge, I can add a cell above. So there are a bunch of parameters. So I could give 2 tuples or 3 tuples, where this is the easiest one, where you just have the vertices that are going to form the edge, or you also give a pair of edges and some other dictionary data, and you can also add single edges and so on. Okay. So here let me go back here and just run this. That's it, right? So now if I create an additional, it's just a graph. It just says what are the nodes and what are the edges, right. And here you go, print nodes of the above graph, number of nodes and edges. This is what I was trying to show. Here you go. Okay, so you do undirected graph, which is given this variable, and what are the number of nodes, what are the number of edges in this graph. And there are other useful commands like adj or adjacency, which tell you what are the nodes that are adjacent to a given node. So, you click this, you say that B, C, D are adjacent to A. If you want to change it to B, you will get A, C, D, F, G. You see that B has the highest degree in this graph. It is connected to 1, 2, 3, 4, 5 different nodes. So, C, D, A, F and G, which is what you see here. Okay. There are other useful methods as well that are useful in graph generation. So, you can add node or add nodes from a list or add a given single edge to the graph or remove a node, remove a list of edges or remove a single edge also. Okay. You should explore these so that you are able to create any graph that you want to tinker around with. Maybe you want to just try out by hand, trying to draw a network and try to find out its between a centrality or something like that. And then you can cross check it by constructing that graph in Python here and using it to essentially see if you are able to correctly reproduce the between a centrality calculations and so on. So how do you generate a directed graph using NetworkX? So this is generated using the command digraph, not just graph. So in the previous example, we just used the example graph. Now we are using the example digraph. We again give an edge list. This means that A is the source node and C is the target node. Okay. And here we go. Let's add. So now let's look at the edges in this graph. So then look at the adjacency, which is essentially a dictionary or an adjacency map, and then you can just look at this or similar to what we did for undirected graphs. So you just look, the outgoing edges are to C and E. How do you generate a weighted graph using NetworkX? You can again use a directed graph and you can just add it as a third attribute. So I say AC3, AE5, BA1, BC3 and so on, and that way we generate a weighted graph. And you use the command graph.add weighted edges from this tuple, this list of tuples. And here you go, now we can visualize these networks. It is not possible to visualize a lot of networks because they can become extremely large, but in this example it is easy to visualize these networks. So let us look at it. So first say figure and axis are plot.subplots, and you also specify a figure size. So this is what this is typically very simple if you have used MATLAB before. This tries to matplotlib is essentially trying to borrow a lot from MATLAB, and here it says set title and so on. So in the three different subplots. So this goes as nx.draw, graph, and then position, axis and keywords, right? And you can say whether you want to show labels and what is the font and things like this. So let us try to run this. Here you go. So this is an undirected graph. It obviously looks different from what we saw in the pictures here, but it's isomorphic to the same graph. These are the same graphs. And here you have the edges as well, right? So you know that BD is 4 and DF is 5 and so on. although there are a few challenges. For example, DC is sort of sitting everywhere, but this 6 is sitting, I don't know, maybe yeah, it's in the middle of this edge, so you can assume it is this. And what is EF is 3, and I think that number is given here. And what about BC is 3, so and that just doubles up here. So I think there are some challenges in visualization, but that's it. So you can read a little bit more about NetworkX visualization here. There are some good examples as well. So for example, let's do one more example that we borrowed from the this graph looks nice. Right. So how many nodes does it have? Right. There are 20 nodes, obviously this being a dodecahedron. And how many edges? Thirty edges. Okay. So now let's look at some network parameters. For example, degree and degree distribution. So here you go. So the degree of node A is 3. So recall this graph here. Maybe I can just repaste this here. Yep. So here you go. So you can see the degree of node C is 3. Degree of node D is 1, 2, 3, 4, 5 and so on. The same as degree of B. Again you see 5 outgoing edges. Okay. What the degree distribution looks like? It obviously is going to look like 3, 5, 3, 5, 3, 5, 3, 5, 3, 1, 2. Right. So you're going to have a bigger spike at 3 and a slightly and a spike of size 2 at 5. Here you go. And no node with degree 4. And you can also look at the density of the graph, directly compute density and clustering coefficient of each of the nodes and diameter of the graph. It's straightforward, it's 3 in this case, and the characteristic path length. So basically this involves a bit of computation and you can compute it as 1.5 in this graph. You need to identify all the shortest paths before you do the characteristic path length computation. And then we can go over to centrality measures. This is fairly easy. You just go ahead and put n extra degree centrality, you get it. Right. So if you look at the documentation, so this is normalized, so you can also get the degrees. Okay. And closeness centrality is here, and between and you can look at the documentation. Which is just n minus 1 by size of g minus 1. This is how the normalization is done. This is something we had discussed earlier in the course as well. and here is between a centrality, where you see that A and C and also G and E are not connected to any, are not on any of the shortest paths. Right? It's imaginable for G, but it's interesting that A is also not the shortest path because it has a very high clustering coefficient. So every pair of nodes that is connected to, every node that is connected to is also directly connected. So this is not going to sit on any shortest path. See, A has a clustering coefficient of 1.0. So, okay. So this was a quick introduction to NetworkX and how you can use NetworkX to compute network parameters, centrality measures, visualize networks, although you may not often do it, and also basically manipulate, load and manipulate graphs of various kinds. I'll see you again in the next tutorial where we will probably look at a few more examples of how we can use NetworkX to tinker around with networks. See you.